Hey guys, today we're going to look at a really interesting and powerful integration trick or technique which applies to problems such as this one. Here we have the integral of x times the arc cotangent of x dx. Now, this video assumes that you're already familiar with integration by parts. So if you're not yet familiar with integration by parts, this video is probably not for you. Come back when you have a thorough understanding of integration by parts. But anyway, if we look at the integrand here, it screams integration by parts. Whenever you have an integrand that looks like something where if you were going to differentiate, you might use the product rule. You have some function of x, in this case just x, multiplied by some other function of x, arc cotangent of x. If we were differentiating that, we would use the product rule. And usually when that's the case, if we're integrating, we would use integration by parts. So a reminder, the integration by parts formula, the integral of u dv is equal to uv minus the integral of v du. And we have this mnemonic. There's a couple different versions of this. The one I like to use is I late. I tell my students it's what they often say when they arrive at school, I late. And what this mnemonic does, we go down the list. I is inverse trig functions, L is logarithms, A is algebraic expressions like a polynomial, T is a trig function, and E is an exponential. And we start with the I, and we go down to E, and these are for choosing what to make the U in the formula. If we have an inverse trig function in the integrand, which we do, we should make that the U. And if we didn't, but we did have a log, we would make that the u. If we didn't have either, but we had an algebraic expression, we would make that the u, etc. But we do have an inverse trig function in this case. So let's go ahead and make that the u. So u is the arc cotangent of x. And then the dv is everything else. Okay, so we've used this. Everything else besides the integration sign. So we have the x, and then we also have the part my students often forget, the dx. So dv is x dx. Now du we get from differentiating our u with respect to x. So du dx is the derivative of arc cotangent of x, which you might have to look this up on a cheat sheet, but it's negative 1 over 1 plus x squared. Okay, then we multiply both sides by dx. And on the left, the dx's cancel. Okay, so there's our du. du is negative 1 over 1 plus x squared dx. And then to get our v, we differentiate our dv. So in this case, it's a polynomial. So x is the same as x to the power 1. We add 1 to that. We get x squared. And then we take that new number 2 and we divide by that. So we get x squared over 2 for our v. Okay, now we have all four parts. We have u, v, du, dv. Let's plug them all in to the integration by parts formula and see what we get. So this integral is equal to u times v. So x squared over 2 arc cotangent of x minus the integral of v du. So that's going to be x squared over 2. And then du, we have this negative 1 over 1 plus x squared dx. Okay, now what? Well, for integration by parts to work, generally we get something here that's easier to integrate than the initial integral. In this case, we don't. Okay, this negative, if I kind of simplify this, we have negative x squared over 2 times 1 plus x squared dx. That's a tricky integral to evaluate by hand, unless we use the trick that this video is all about. So we got an integral that's hard to evaluate, so we're going to use the trick. Now, all the steps that we've done up to this point, one of those steps had a little shortcut. We didn't answer it completely exactly correct like we should have. We took a little shortcut. So before I tell you, see if you can figure out which step was that. You might want to pause the video, go back through all the steps we've done so far, and which step did we take a little shortcut? Can you find it? It's actually when we calculated the v from the dv by taking the antiderivative. Okay, what we're actually doing here is when we take the antiderivative, is we're evaluating, let's see, we're evaluating the integral of x dx, okay? And when you evaluate that, you don't just get x squared over 2, because it's an indefinite integral. You get x squared over 2 plus c. So let's go ahead and make that change. V is equal to x squared over 2 plus c. Now remember, the reason for this is when you take a derivative, okay, you get the same derivative no matter how high or up the original function is along the y-axis. Okay, if I take the derivative of x squared, I get the same answer, I get 2x, as if I take the derivative of x squared plus 5, I also get 2x. So that information, when you take the derivative, is lost. The information about how high up or down the original function is along the y-axis. So that's why we add this plus c. No matter what the value of c, c can go from negative infinity to infinity, any real number. If we take the derivative, no matter what the value of c, we're just going to get x, okay? So this v is true for any value of c. C can be any real number. And what we can do for this trick is we can set c to any particular value that we want just to make the integration work. So what I'm going to say is let c equal, and you might want to pause the video again here and see if you can figure out what value of c am I going to choose. And to give you a hint, what I want, if we go back here to this integral, I want something to cancel. I want this 1 plus x squared to cancel. So think about that. What value of c would you choose in order to make it so this 1 plus x squared cancels with something? And the answer is going to be 1/2. Okay, so now we get a new v. It's going to be x squared plus 2, sorry, x squared over 2 plus 1/2. And we have a common denominator here, so we can simplify this to x squared plus 1 over 2. Okay, and now you see that x squared plus 1 in the numerator, which is going to cancel with that 1 plus x squared in the denominator. Okay, so let's go ahead and cross this one out. And go ahead and use the entire integration by parts formula with our new v. Okay, so the first part is u times v. So now we have x squared plus 1 over 2 times v, or times our u, which is arc cotangent of x, minus the integral of v du. So now we have x squared plus 1 over 2 times our dv, which is negative 1 over 1 plus x squared. Oops. Let's just call it x squared plus 1. Doesn't matter. Dx. Okay. Now there's always implied parentheses around the numerator of a fraction or the denominator of a fraction. So this is actually factored. So we can cancel the x squared plus 1s. Remember, you can only cancel factors. You cannot cancel summons. I don't know how many times I need to tell my students that. But anyway, after this cancels, the only thing that's left is this negative 1 over 2, which is just a constant. So we could actually pull that out of the integration symbol outside of the integrand, or sorry, outside of the symbol, just in front of the integral. Or you could leave it in, and you can evaluate the integral of negative 1/2. Either way, really doesn't matter. So let's rewrite everything, x squared plus 1 over 2 times arc cotangent of x. Okay, I'm going to pull out the negative 1/2. So when I factor out the negative, it's going to cancel with this negative to make it plus. Okay, so we have plus 1/2, the integral of nothing. Everything canceled or got pulled out, so that means you have just 1. Okay, and let's go ahead and evaluate that. This will be the final answer here on this step. So x squared plus 1 over 2, arc cotangent of x. Okay, the antiderivative of 1 with respect to x is just x. So we have x over 2 and it's plus, and it's an indefinite integral, so at the end we add the parameter c plus c, where c is any real number. Okay, so final answer. The integral of x times the arc cotangent of x dx is equal to, it evaluates to, x squared plus 1 over 2 times the arc cotangent of x plus x over 2 plus c. Now, there's one final thing I want to say about this. If you try to look up the answer to this integral, what it evaluates to on a solver, you might get something that looks slightly different. I actually use Symbolab just to kind of check my answer. And you can see here that I got something that looks a little bit different from our answer. They have this negative arctan here. First of all, they distributed out the fraction, the x squared plus 1 over 2. They made that x squared over 2 plus 1 over 2 and distributed that out. But then one of the cotangents they have as arctangent, one of the arc cotangents. This would be, if you look closely at it, this is the exact same answer that we have if you replace that negative arctan by positive arc cotan. Now, is our answer correct? Is this answer correct? Are they the same? Well, I went ahead and graphed both answers here on Desmos. So ours is the one in green, and the one Symbolab is giving is in black. But looking at the graphs, they look slightly different. However, they look like they're the same shape. Just remember that because of that plus C, or in the case of the Symbolab one, I use plus D, just because C was already taken. That could be any real number. So the evaluation of the indefinite integral isn't the graph you're looking at. It's the family of functions when C goes from negative infinity to infinity and hits every value in between. So as we increase and decrease the value of C, all of these are the solutions to the indefinite integral. And we can do the same thing with the one from Symbolab. And you can see that this family of solutions, as we move the C and D up and down, is going to give us the same set of solutions as this one. And I actually kind of went through and I found that arc cotangent of x is the same as negative arctan of x plus pi over 2. You can see that if I turn both of these on. They are the same function. Okay, so that's why the answers look a little bit different, but they are in fact the same.